Hey,
Hey, how are you doing?
it's okay.
Wow, so many people. Okay, thank you for the reminder, Shasha. So this is recording now. I was saying I am Pelayo. I'm a postdoctoral researcher in the group of Ted Sargent at University of Toronto. So today we'll be having some examples and some small workshop on best practice to make better figures. Most of you in this audience already make kind of good figures, so this is more like some small add-ons, some small guidelines to avoid making big mistakes in figures, trying to improve your chances of readability and message conveyance. So the agenda of today's talk goes as follows. We will start with some basics on figure communication. We will follow with some aspects of figure design, some aspects of figure formats. This is also very important. Some tools that are very useful in this context, and some tips and tricks. This will be all guided through different examples, and I will at some point ask for your input. At any point, please, if you have any question, just feel free to write it in the chat, and we can go question answer live. So there is this saying that states that a picture is worth 1,000 words. We get most of our daily information through images. Our brain is accustomed to receive information in the form of images, so it's easier to convey information in this way. In this context, in our context of science communication, it is very important then that we choose these 1,000 words with care. It is important that we communicate what we want to communicate and avoid communicating unnecessary stuff. So a good graphic should have these aspects, should have clarity and precision, lack of ambiguity, and especially in science, do not mislead the reader. It has to be efficient. That's very important. It has to avoid noise in the figure, unnecessary items that do not contribute to the role of the figure. Show only what is needed, and I think it's very important that the figure is easy to understand in a short time. So think of when you are reviewing a paper, when you're reading a paper, the more time you keep looking at the figure without understanding it, the worse your mood is, and the worse the reviewer comments are too. The last aspect of all of this is the aesthetics of the figure. It has to be visual appealing as long as the other aspects are addressed. So we have some nice figure here from a paper from Moscowitz group, and it's a nano paper. We all deal in our papers with composite figures, several panels. It's important that these panels are balanced, so you don't have scattered panels around which are not connected to each other. Have to follow some flow, be logic. So don't have a panel showing absorption of one material in one side and the other plot showing, I don't know, whatever property that doesn't have anything to do with this, a cartoon not explaining anything. It importantly has to be consistent in colors and labels, same fonts, same sizes, and be legible. For this particular example, which is kind of nice, there are also some things that can be improved. So now we will pause my talking for a while, and I welcome you to spot any things that could be improved. You could also acknowledge some things that are right, such as in panel B, you see that there is logic. You have a schematic of some nanorods, and to the right of the schematics, you have a SEM image of the corresponding schematic. And as you proceed through fabrication steps, you have the corresponding SEM image. This is very nice. But now I open the floor for people to spot what is not so nice and what can be improved. So you have anything to say, please write in the chat, and then don't be shy. Okay, Shasha is saying that it's too busy. Maybe, Shasha, you can open your mic and comment on this.
Well, so overall here are 6 panels, and it's kind of okay, but what I usually don't like when among the 6 panels, you get 6 graphs. That's just impossible to read. So here it's not too bad. But at the same time, these graphs are hard to understand without text. I guess that's my biggest problem.
That's true. Okay. Any other comments? Okay. Hi, Maksud. So Maksud is saying that C and D are too similar. Can you comment on that? You can open your mic if you want.
Yeah, hi everyone. Yeah, I think C and D are very similar, and those that information that is given on panels doesn't clarify the difference between those.
Yeah, you make a good point. So in panel D, they show front illumination of a device and back illumination, but they don't show what does it mean actually. Look, in panel A, there is some schematic of a device, and then they refer to front illumination, back illumination, without saying what kind of direction is the original illumination. They are also very similar, C and D, you're right.
Yeah.
And as Shasha was saying, this is not easy to understand without text. So this is a figure that can be understood by the community, perhaps, that has experience in this kind of plots, but it's not straightforward. Okay, Pina, he makes a really good point. Pina, you can open your mic and comment on this.
Well, it's just like you mentioned before, in terms of the color scheme, maybe it would be better if we keep the same color schemes throughout all the figures. And it seems figure C is red and black, while figure D and E are red and blue.
Okay. Good point. So in general, this is a very important aspect to keep color consistency. However, in this case, and I was also drawing the same conclusion as you did first, but you realize, like in the panel C, they compare white and visible light illumination. So if you were to use the same color code in panel D, it might give the impression that you are also comparing these things. So Peter says that 2 different styles. Okay, so we will address this later. So as long as the red line in panel C and the red line in panel D were similar, that would be okay because they were referring to the same aspect. anyway, it's very noisy in case, as you see. So there is not clear correlation of what we're showing or what's important in what you're showing. So also regarding to your Peter comment, to your comment, Peter, on panel E, they show a different line style suddenly with symbols compared to another line style for absorption, which do not necessarily actually match the color code shown in panel C. So this is also an important aspect. And I say panels do not follow each other, and that's a good point too. So if you read the figure, normally you read from top to bottom or from left to right. So you start from A, you go to B in the right, and then suddenly you go back to C. So a better arrangement of the figure, in my view, would be placing panel B underneath panel A and moving panel C and D on top of panel E. Sasha, you want to comment on the vertical arrangement point?
Well, it's just a little bit unusual. So 6 panels usually fit perfectly if they are placed horizontally. They will fit perfectly in a page size. I'm not even sure how they managed to put this into page.
So I think this is in Etch Nano. It says 2/3 of the total width, I think, but I don't remember now. That's a good point. But okay, we should move forward. But you see, this is a good example of a figure that is looking nice actually, but it has lots of things that could be improved. Another figure, this is from Min Yan's paper in Nature Energy, that kind of looks nice. Sorry for the resolution. It's just coming from a screenshot of my screen, showing different aspects of a luminescent solar concentrator. Again, is there anything that's wrong here or that could be improved? Too white, so too blank space.
Well, just the figure itself, even the I don't know, platelets, what is this?
Yeah.
Too faint.
That's a good point. So the main point that I wanted to show here was you see in panel B, there are different layers of perovskites with different colors going from blue to green. And in the panel C, there is a corresponding translation in these color codes, which I realize now that is not perfectly accurate because the color corresponding to n equals 3 in panel B is not the same color corresponding to n equals 3 in panel C, but the color corresponding to absorption. I mean, that's not a big deal, but that's something that could be improved. Contrast. Okay, this is true, like contrast perhaps could be improved a bit. Any other comment? Okay, Maksud says too many processes. You want to comment on this?
Yeah, sure. I think it's hard to read from left to right or from top to bottom what is happening first, what's happening second. And because you are describing too many processes, I kind of start looking at the circle in the middle, and then I start looking around and I'm lost.
It's a good point. So what's the first thing you spot in a figure? So you look, what draws your
circle?
It's that circle. That's right. Maybe it's because it's highlighted in red. So, well, in all cases, we realize that what we miss here is the caption too. So because we usually combine our input from the figure with the caption, and this will be covered later in the presentation. But again, the point is like any figure, even if it's looking good in principle, can be improved. This is another figure from the previous paper, easier to follow perhaps, all data driven. And there are a few things you can spot here too. If you spot anything interesting, you can write it in the chat. So what I like, for example, in this figure is that panel B saves a lot of ink. It doesn't have like this fill color, which is sometimes not needed. And it says different font size. Okay, that's true. There is a different font size in the X label of panel B. Maybe something else too. Any other comment on this figure? Do you spot any problem on panel B and C? Poor color selections. Can you comment on this, Yehu?
Can you hear me?
Yeah.
Yeah, the color looks not that fancy yet. So usually, I think it's as last time Brandon mentioned in his talk, and it's been nice if we can choose a nice series of color and in the picture. So I think this black red color is doesn't look very nice for me. Yeah.
So which colors would you like? I mean, it's quite simple plot, so not a lot of different information to convey. So what colors will you choose?
Yeah, you can make it a little bit fancy, or you can increase the transparency of these curves, or you can add some shadow, or also the color consistency is not good because the red in the figure B and the figure C actually is not the same red, and yeah, it's some very detailed stuff, but yeah, but my feeling is doesn't look very nice.
I think that, well, everything is oxygen should be red. Yeah, that's true. Like if that's the main aspect, which I think is lacking here, is like there is not a connection between panel A and panel B and C. So in panel A, you show hydrogen evolution in black square symbols, whereas in panel C, you suddenly change the color set for hydrogen to be red with a different symbol to should shade the bars in B. Yeah, I mean that's again that's a more aesthetic. I think you could use some shading there too, if that improved.
Yeah, exactly. Yeah.
But the main problem to me looks to me is the poor choice of the exactly opposite choice of colors for A and C. Actually, a good thing that could be added is in panel B. In principle, the addition of the three bars in the center corresponding to the 300 to 500, 400, and 600 nanometers should in some way be related to the total hydrogen production under AM 1.5 illumination. So it would be nice if they could show some, I don't know, combined hydrogen production with a wider band too. I like this Miao in recent Nature paper. He introduced this kind of plots, like when he shows different bars, and then he shows a wider bar consisting of the addition of all the bars. Okay, so thanks to you, Han, for bringing this paper. So, what can be improved in this figure now? I think we have like more than 50 people in the room, but I think only a bunch of people is actually speaking, so don't be shy.
I think they are not constant. The caption inside the picture, the left shows the electrical energy and the right one shows electrical. And yeah, I think also because the place here is quite limited, actually, I think probably they can remove this part to the figure caption and to just put color there. Or they can use some, shorter words and to make it looks better, because I think they put too many words in one picture. Yeah.
Yeah, I think Andrew says no idea what they try to convey. That's actually very true. It's difficult to understand, maybe because you are not very much into this, I don't know, hydrogen cracking stuff. To me, the most appealing, not appealing actually, so the most the weirdest stuff here is the fact that they introduce this kind of as Hugo says, this kind of fake 3D shade that adds information that it's not needed. So you don't need to add this kind of shade in the center of the bars. Again, you have to minimize the information that does not convey the message that you want. So these shades of light in the center of the bars are totally useless. It's taking time and energy for you to understand. Labels A and B are not in the same. I don't get this topping. So first, going to Sam's comment, yeah, the slightly gray background is a bit strange too. So no need to use this gray background at all. All fonts are bold. Sasha, this is true. So I find that most graphs that people make, especially using Origin and other suites, they tend to export in kind of bold fonts, which is not needed, is actually bad. So you use boldness when you have to highlight something as a way to strengthen some particular message. So if you just use bold fonts everywhere, you're losing your point.
Exactly. So it should be in one place, which is fine. So usually I see people try to use bold font when they see that the font is too small, and instead of increasing font size, they're increasing the boldness,
yeah,
which is wrong, I think.
It's wrong because it also, I mean, a font with a given size, if it is small already, if it is bold, it will be more difficult to understand, even if in that case, because if you print it, it will be way more difficult to understand. Okay, so moving forward, thank you all for your comments first. They were very, very useful, and you already have a very good idea of what's good and what's bad in all of these figures. So there are different types of graphs in our community focused on photovoltaics, on catalysis, on photocatalysis and others. We are mostly used to using a particular subset of these different types of graphs, such as line plots, bar plots, or some like fancier radar plots, or arc diagrams for impedance, statistics using some kind of box and whiskers, etc. But we are using a very narrow set of graphs. We will cover this aspect later, but what I want to say is that there are different types of graphs, and it is very important to choose the most accurate and the most effective way of plotting your data. If you go to this website, you can find good examples for all of these different types of plots, and you might find inspiration if you don't know how to plot your data, if your data is very complex and requires some fancy plotting. But in general, the simplest types of plots are 2D plots, where one plots a series of data. It's like an array, one-dimensional array, which can be, for example, one observable versus one variable. For example, Faraday efficiency versus time, or power versus time. It could be also an observable versus a label. So it doesn't have to be all in the same domain. It can be something quantitative versus something qualitative. So for example, power conversion efficiency versus sample. How many observables will you show in a plot? That of course depends, but if you imagine you have a 2D plot with different lines, how many lines do you think are the maximum that you would see acceptable of plotting there? Four looks like a good number. So 3 or 4 to me looks like the most, like the biggest, the largest number of graphs that one should show in the same plot. If you have to show more than this, it will very likely be the case that you have to use a different plot. So you can focus on a smaller number of observables in one plot, and then develop a more complex plot, understanding more correlation between different observables, such as current versus voltage, Faraday efficiency versus current, or this kind of things for different samples. So in this nice plot from Maral, who I think is in the audience, can you tell me which are the observables? Okay. Anything else? So we have EQE, we have thickness, red colors. We have EQE for different thicknesses, but this is a very complex plot actually, because EQE depends on the wavelength. You see, for different wavelengths, we have different EQEs. EQEs depends not only on the wavelengths, but also on the thicknesses. So for different thicknesses, you have different features here, different peaks that are at different positions, that have different values. So it will be better to improve, I mean, the readability of this plot if you just picked some 2 cases here, perhaps, or 3 cases of EQE for different thickness, and then in a separate panel, you could convey the message that you want for the observables that are actually more important in this plot, which are, for example, EQE as a function of thickness. So you could have a simpler plot, again, with only one line showing EQE as a function of thickness. You might also be interested in the position of these peaks, the position of the peak at whichever band as a function of thickness, and so on. So when your plot is very messy or very complex, you can always think of ways of simplifying it and then maybe extending it into, unfolding it into different graphs. So this is also a very interesting graph, also from Min Yang's paper, which has many different things going on here. So can you comment now which are the observables? What is the plot saying here? It shows absorption, right, and photoluminescence as a function of wavelength for 3 different samples, which are samples having different stoichiometries, x equals 1.3, 1.1, 0.8 in this formula, right? Yeah, Maksud, what do you mean by x?
Yeah, you mentioned those x equal to 1.3, 1.1, 0.8.
So this is like the label for each of these traces. Tapeng, he asks, what is S? So this is actually a good point, because this plot,
there is a S in the bottom figure, but we don't know what. Yeah.
That's right. So in this example, because the plot was kind of very messy already, we identified the metric that we then analyze on a different plot, which is S, which in the caption stands for self-absorption. So then in the next plot, we plot this figure, this figure of merit S as a function of other parameters. So it's a way of introducing this parameter and then exploring it further.
Okay.
So there are many examples of things that can be improved. I will attach, maybe it's better that one of these groups should be dashed lines. That's true. So perhaps the one in the middle should be a dashed line to improve readability. I'm attaching in the package with this video, there will be different resources. One of these resources is a nice presentation made by Vigil and Kamat. Kamat is the senior chief editor of ACS Energy Letters, and they have a nice presentation showing some examples on good and bad stuff. So for example, in panel B, what do you think it is weird? What do you think is weird here?
It already says what's weird.
I know. So you're just comparing the EQE versus the label of something, and you just arrange these labels in a convenient way to show some kind of trend, which does not necessarily happen actually. So a better way of conveying non-causal data, which is just some metric compared to some label usually, is using bar plots, such as the ones showed here in the right. Should avoid abbreviations. That's true, but I don't know how can you otherwise maybe sometimes identify some labels. But there is also something wrong in the plot in the right. What is wrong in the plot in the right? Yeah. No need for 3D, no need of showing 3 different colors at all. So having a 2D bar plot is always much better than showing this. Andrew Prop says better suited for a table too. Most bar plots can be also shown in tables. I think that depends on the particular paper you have already tables or too many figures or not. But that's also true. Like you can convey in a similar way the information in a table, although like again the visual appearance of a graph is always better. Okay. Now, how can you add more information to a 2D plot? We have different tools here. You have the line width and type, which can be used to differentiate different samples, but it also can be used to add little subtle information to try to reinforce your message without distorting the information that you want to convey. You can also use different symbols and combine these with lines to showcase what is an experiment, what is actual experimental data, what is a guide to the eye, what is a fit. You can use different colors, and there is also a lot of psychology for the colors that you choose, in the sense that different colors showcase different importance. It is typically the case that black or gray colors are better for references, and more vivid colors, reds, blues, or these families of colors are better for the samples that you want to compare to the references. Shadings in general can be used to embellish and give some prevalence to one of the plots, one of the traces of in the plot that you're showing, but in general they are not needed, so you have to use them with care. Just showing you one example where the combination of points and lines is kind of cool. So you have a lot of experimental points where you measure temperature as a function of date. There are other problems in this plot, of course, such as the x-axis. But on top of this rather scattered set of data, apparently for temperatures, you spot a trend, which you highlight in a thicker line, which is more solid to the eye compared to the background gray color. As long as you identify in the text or in the caption, how do you calculate this? It can be, for example, a moving average, it can be a model that you have developed. That's always good and actually very nice. You can see a lot of these data representation techniques now. If you're following the media for the COVID cases, there is a very nice journalist in the Financial Times who is doing this kind of always not only fancy but very useful plots using different techniques. So it is always good also to look into plots that you like, not only in your scientific community but anywhere, and bring ideas that you like. So for lines, what aspect can you change in the lines just to improve comparison and to improve readability? In the left plot, you have different lines with the same line width. In the central plot, you have the same lines, but the first and the last line have different line widths. So you can use this to improve readability when you have a bunch of lines, to show a trend, to show what is the first and what is the last line in your analysis, for example. So people have, as Maksud was saying, when you look into a figure, you have to identify where's your eye going first, and when you drive the eye to a position, then you can drive it to the next step. That, I think there's a science behind this itself. It takes time and experience, and I think, yeah, it's worth devoting time to learning how to do these things. On the last panel, we use some shading. So it's absolutely unnecessary here, but I myself even use it sometimes. When you have little lines, not a lot of data, and you have to embellish your figure, this is a way of, I don't know, making it more appealing. Also, it gives the sense that the sample on the top is superior to the one in the bottom, which, as long as the data is accurate and it makes sense, and you don't distort the message, that's something you can use. A good example I like combining lines and areas is the case when you have a set of data and error bars. So you could plot this data in the way shown in the left, consisting of just spare points with some error bars, or you could just also join these error bars, defining a shade behind the main line of the data, and this gives you a better sense of the trend, actually, that rather than seeing these areas here, as long as, again, it is clear what is the experimental points and what is the interpolation between these points, that should be okay. Do you have any comments or any feedback on this type of approaches? Okay, so moving forward to more complex plots, I mean, if you read a plot, it is much better to understand in general 2D plots than 3D plots, but in some occasions we need to use 3D plots. 3D plots are needed when you have several observables that you have to compare versus different variables. They can be discrete or quasi-continuous. You could have points, or you could have surfaces, or you could have 3D volumes that you want to plot. There are different ways of plotting this data, so you can differentiate them in different ways. For example, you can have color-coded representation. We have 2 dimensions, X and Y, which could be a space, but could be something else too. And you represent the quantity of interest as a color. So this is a color map. You have a 2D image where you have X, Y axis, and then in the Z axis, going out of the paper, you have the color. This can be also implemented in a height coded scheme where you have X, Y, and you have another magnitude, which is Z, which just tells you the amplitude of a variable, for example. But there are also more combined, weird and abstract plots where you have both X, Y, Z, and then you also have a color. So we'll see some examples of this. So you could plot this data in different ways. For example, in the left, you see a magnitude plotted against X and Y. I don't know what are the units. And it is the case because we are dealing with discrete data that you usually have a matrix of data, right? You have a matrix you want to plot. In this case, maybe it is like 20 by 20 matrix you want to plot. So you don't have like a continuum of data that you want to plot. This data can be plotted in different ways. It can be plotted in a 3D way, as you see here, where you have both color and height information. But that doesn't help readability, actually. I think it introduces more noise. So in my view, it's much better if whenever you have these plots, even if they look right and nice, they look right and nice, but they don't serve their purpose, which is conveying information. So it is usually more useful if you represent this from a top perspective, such as Maksud was doing in his very nice Nature Materials paper here. There are also different ways of plotting the data in terms of how do you represent this, even if you are showing it in a 2-dimensional scheme. So you could have faceted shading where you have like lines between the pixels. This actually is very noise. Normally you have unnecessary information in terms of lines between the pixels. You can use flat shading. It's this one here, which is the one used by Mexud here. And you can also have interpolated shading. So when you have enough points, you could increase artificially the resolution of your image by saying, okay, what is the point that would be, what is value that you will have in this pixel if you actually had this pixel, and then you can interpolate it in different ways. That is actually very tricky. So in general, not recommended because it can lead to misinterpretation. We will discuss in next slides about the selection of colors, but I wanted to highlight here this figure from Mexud, which I remember when he was drawing this figure. When he was drawing this figure, I saw it in his screen. I was instantly appealed by I mean how good this figure was looking. I asked him, I remember, oh, this is your next science paper or something like this, because to me these figures looks like very interesting experimental data shown in a nice way. You have in the top the quantity that you are measuring. I think it is luminescence as a function of x and y coordinates. You have in the central row another experiment when you include time, and then you have in the bottom a model that actually supports experimental data that you were showing. But there is a clear difference between experimental data and model data. Any comments on these figures?
So this light blue color, I don't know if it's made on purpose. So sometimes, well, maybe it's to make it more visual, but it's recommended to keep the brightness, like, so if the value is growing, the brightness should be growing. And here this light blue is just a bit too light. So on the top picture where you have like violet color, that seems more appropriate.
Mexud, any comments? You are.
It looks like Sasha was not a reviewer, so I'm very happy.
Okay.
Yeah, I think it's just to show the front of photoluminescence in dimensions. If you remove blue color, so that the panel D would look very, it would not show what we want to show. Yeah. But it would be hard to see the front.
Yeah, so every type of plot has to be tailored depending on the message you want to convey, and we will now discuss more about this choice of colors. But it is very important, especially in these panels, to use the right choice of colors. A lot of people here is doing transient absorption, showing these maps, and other experiments, TA experiments. So it is important that you choose the colors that help you, not that destroy your message, actually. So more complex plots, which nobody can understand. So it's already difficult to understand 3D plots. So this is like a 4D plot where you have some quantity against X, Y, Z, and then you have information in the other dimension, in the color space. So it is very hard to understand these plots. In general, they are usually employed in tomography, such as in this paper of Hao Tian. He loves using this kind of fancy plots, but actually don't serve your purpose unless you complement this with slice of data. So you say you take a slice of this 3D, 4D image and you plot what is in there, and you show that the different slices, maybe you have different arrangements of different atoms. I think this was to study nickel or nitrogen doping on carbon-based systems. So this is good to show that this is homogeneous, but this is not telling you anything else, actually, not even that it is homogeneous. So then to choose your type of graph, what you need to think of is your information clearly conveyed. So you have to tailor your graph for your audience. So is the plot you use common in your field of research? So if you come up with a very fancy plot that only you can understand, this will be very difficult for the reviewers and for the readers to understand, and your paper will not be accepted very easily, and it will not be cited very easily. Fancy new types of plots, I think, are nice if needed, but more especially can be useful for review papers, perspectives these kind of things when you introduce a new idea, you introduce a summary, you introduce a bigger concept. You have to remember, as you also review papers and read papers, you have to have some empathy. So your reviewers and readers will lose energy if they have to use a lot of time to understand your figure. So the easier that your figure is, the bigger chances of success you'll have. So regarding the use of fonts, so that depends a lot on the fonts you choose, but the fonts, of course, have to be legible. Depending on the type of font, this means that your font cannot be by any means smaller than 10 points. That is also depending on the software you use to make the plots, because sometimes you use the software to make the plots, you make the plots this big, and when you export the plot is like 20 centimeters wide, and then you have to shrink it to the paper width, and then the actual font size in the end is 5 points. So you have to craft your figures thinking of the actual dimensions in the paper, which is normally around 16 centimeter width. As Sasha was saying before, don't bold everything, because then you defeat the purpose of bolding. This is only a tool to provide contrast. It is very important to, I think you all know it, but I just say it so the presentation is consistent, to use an appropriate type of font and to try to use the same type of font across the board. So use whatever you want, but be consistent. Try not to use more than one font. Certain fonts are preferred normally. I just highlight some of my favorites here, which are Segoe, Helvetica, Arial, and others. You already have a lot of good fonts in your softwares for sure, but if you want to look for more fonts, there are different resources. I just put here this website called DaFont, where you could find a lot of good fonts for free. Again, this is based on this CAMAT good example. Different fonts, different sizes. You have to keep consistent formats. That's a good point in the left. So I see some people prefer to use the name of the variable and then between brackets the unit, and some people instead use the variable slash the unit of the magnitude that you're showing. So in any case, just choose whatever you prefer, but be consistent. It looks very weird if you just combine these different types of plotting of labeling the data. So now, just to choose colors, that's science itself, and everyone has their own style. But in general, you have to remember that the color choice have to help your purpose, which is have to convey the message, has to be visually appealing, but this is not the ultimate purpose. And you don't have to remember that black color is always good in any combination. So depending on what you want to show, you can use the color wheel just to create your color set, your Pantone of colors that will serve you to highlight what you want to show in different plots. So you can use complementary colors. If you choose colors that are opposite in this wheel, for example, in this case, red and green, this can be used to show differences between data sets. For example, if you compare red and green, even if you print it in black and white, it will be easier to spot the differences. If you were to move this wheel a bit to the left, you would compare this slightly lighter red to this blue color, for example. It is rare that we have just 2 lines to choose colors to. So when you have to represent a more complex data set, there are different ways of doing so. So you have, for example, a trend or a traces that represent the same sample under slightly different temperature, for example, or something is just a gradual change. You can use analogous colors, for example, colors that are near each other in this wheel, from yellow to dark green, for example. You can move it around and choose a different color set if you want. So this is again good if you want to show similarities, you want to show a trend. But then you want to show samples that are different, again, just like an extension of panel A. It's better to use what is called the triad colors, or just it doesn't have to be a triangle. You could be using a square or some other polygon, but use colors that are equidistant in this color wheel. This will help you offer some variety without using colors that do not match at all. For example, I find horrible combinations of colors sometimes, and trying to think of some horrible combinations Of course, maybe you can tell me some horrible combinations of colors that you don't like.
Well, sometimes it's important to remember about the colorblind people as well.
Yeah.
So green and red actually are not recommended, and Nature Communications, for example, explicitly says it's forbidden. So they tell you to use like red and cyan instead.
Yeah, that's a good point. So there are also resources for that, like to craft your plots for colorblind people. In general, I think if you craft your plots thinking of black and white, that's always best. So always have features that could identify your different lines if they were printed in black and white. This is also very important. You use your plots later to do in patents. For example, in patents, everything has to be black and white. So you will save a lot of time if your plot is already black and white compatible. Bing Chen is sharing some of nice information about colors for colorblind people. This is already, I think, in the additional resources I had prepared, but I'll just be sure and copy this link into the document as well. Thank you, Bing Chen.
Yeah, one more comment is like I always complained when I lived on a black and white printer and didn't have color. Your colors should print distinguishably into black and white.
And you have to remember too, like if you choose very similar colors, some of the screens or even some of the printers do not render the colors sequentially. So you need to take into account that you don't have to choose very similar colors because they might be rendered in different ways in different systems. So now going back to data representation a bit more, we have here the same data plotted with different color maps. So, okay, any volunteer tell me what is good and what is bad for each color map? Kevin Chen also shared some data for printers and stuff. Thank you. Okay, that in this example, you can see that depending on the color bar that you choose, you could hide a lot of relevant information. If you look in the left plot, you don't see up to the same depth these oscillations that you see in the other plots. So they disappear rather fastly here, and you don't see these higher frequency features here in this image. If you use a diverging color scheme, such as this one, because you have something that is oscillating, sometimes when you have positive or negative values, it is good to use diverging color schemes to showcase what is the threshold and what is above the threshold and what is below the threshold. So in this case, what is positive is red, what is negative is blue, what is close to zero is white. These type of plots, the diverging plots, are very useful, for example, when you are working with TEA papers, techno-economic analysis papers, when you want to show that only above a threshold your system is profitable, for example. So it's good to show thresholds. There are many different ways of choosing these types of color maps. I also left some links in the resources. So depending on what you want to showcase, you might go one way or the other. But what is typically not recommended is to use the standard color set that's coming with most software suites, which is the jet color scheme, which is like a rainbow color scheme, which is providing not necessary colors and often leading to misrepresentation. So you could see in the left plot, you have different examples. I think this is some images from some cells or something like this. So the rainbow scale is introducing artificial information. So it's actually not helping you to convey anything which is related to the data. And again, I want to show the nice figure from Maksud in the right. So again, there are different ways of choosing these colors depending on the software that you use. So sometimes it's very useful, again, thinking of printing, thinking of colorblind people, thinking of improving readability, to use contour plots. So contour plots, on top of the different layers of colors, they add lines with the values that represent this isosurface that connects the points with a similar value. You could see here different colors and lines with a label of 0.5, 0.9, and going outside the circle. So depending on the plot, you might think of including this if it doesn't make your plot too messy. So this is good, again, for example, in the context, again, of TAI analysis, it's very useful. So to choose colors, there are also a lot of tools. You could find some tools here. So you could select what you want to show, and then you can move these colors around until you are satisfied. Also taking into account the other considerations that we have said about color blindness, and then extract this color set and use it in your preferred plotting tool. In MATLAB, there is a tool called Color Map Editor. You can just write it in your console, which pops up this window, which allows you to define your customized color set, color map. So you could introduce or change colors along this axis, and you also have some defaults here. Just again, like unidimensional, diverging, super weird, such as this one, like the lines or the prism. I don't know who is using this kind of color schemes. I think maybe people in sociology or some you know, population-related aspects. But there are different options in other softwares too, such as in Python. There are even more options, I think, in the library Matplotlib. I don't think Origin is very good in handling 2D sets of this kind of plots, like 3D plots with a top view, so 2D plots with colors. But anyone using Origin can comment on this. I only see people complain about Origin, so I don't know in terms of this kind of plots. So if there is something for Origin, you could please just put it in the chat, or you were okay. That's good. So you have a link or something into this, we can add it in the resources then, being that's helpful. Okay, now a bit of file formats, and then after that we can go to some specific examples. So there are different types of figures. So one can have vector graphics. Vector graphics are defined in terms of two-dimensional points, lines, and geometry. So you have polygons, you have different shapes. You could think of storing information in the form of equations written in text. Rastered graphics, on the other hand, they are just like a matrix. You have a matrix that where each pixel represents, each item in the matrix represents a pixel with color or with other property. You could see the main difference of vector and bitmap raster graphics is that vector graphics in principle are not limited to resolution, because you have the equations of the things that you're plotting. You could just change the resolution arbitrarily. Bitmaps, on the other hand, are limited by the final size of the matrix that you render, that you export. Okay, based on this broad classification of files, there are a smaller classification, I mean more narrower classification, and different file formats exist. For raster files, bitmap files, the simpler file format is bitmap, BMP, and TIFF. In this approach, all information is stored in a matrix configuration. The data is not compressed. It has high quality. It's a large file, but the resolution is fixed, meaning that once you export the data or whatever, it is fixed. You cannot zoom in arbitrarily. JPEG was introduced, I think, in the 70s. There were a lot of discussions and litigations about patents. This is a lossy compression, meaning that it does not save all the information, but it destroys. I mean, it discards some of the not so relevant information based on the discrete cosine transform. So you could think of a Fourier transform where you just discard the frequencies above a threshold. So you just keep the most relevant stuff that your eye can distinguish. The last, which is to me the best, is PNG. So portable network graphics. They have lossless compression. And the compression that they have is based on pixel correlations. For example, if you have a lot of areas with the same color or similar colors, importantly, it also allows for storing a transparency channel. So you could have, in this example here with the dices, these squares in the back, they are the transparent channel. So you could just bring this image on top of another image, and it will be just rendering the dices on top of a random background that you want to use. So that's a very useful file format. Regarding vector file formats, the first original file format for this was EPS, which nobody uses now, I think. So data in EPS was stored using an old protocol, an old format, which is called PostScript. Most commonly now people use SVG, Scalable Vector. Sasha says never use TIFF and bitmap. I agree, but you know, in some journals they encourage you to send TIFF images. I don't know why. Like, yes. So SVGs, data is stored based on XML. You have the information in text, and you don't lose any information. And this can be edited very easily. It's also in agreement with the W3C standard, which is the web standard. And they are compressed again based on text, so you don't lose information. And last but not least is the PDF format, which you are all aware. So this was created by Adobe, but now it's royalty free. And it can bundle a mix of data. It can contain SVG information, vector information, but it can also contain raster information. Windows doesn't like SVGs. SVG or SVGs? SVG. Sometimes, I mean, you have to have your editor. You cannot just, there is nothing by default in Windows to use SVGs. So before we go into some specific examples, I just wanted to summarize what I think, yeah, Andrew's right. Yeah, Inkscape is awesome. We will discuss later about Inkscapes. So a quick protocol checklist for your figures. I would start by describing with words what the panel that you are making should show, and even write it down. Identify what is the observable and what is the variable, then select a type of plot. Be sure that you use the axes and labels properly to maximize differentiation, and then plot your data. Then revise the plot. Does the plot tell your message? And it is difficult to decouple yourself from your memory. So you made the plot, so you already understand what you are plotting. So sometimes it is much more useful if you could show your plot to a colleague who could give you their feedback, because they might not necessarily be aware of the experiments that you've been doing, what you want to do. So that's, to me, that's the most useful problem that I also do. When you make a figure, you know what you plot, but you have to keep in mind that the reader doesn't know what you plot. Then you can iterate. Can you remove something in the figure without affecting the message? If you can do, it might be the case that the figure will look better if you just did it. So just remove it and keep iterating until you cannot remove more. Then in the end, show it to your doc. If your doc doesn't understand, start over. And again, repeat with a colleague who is not necessarily in the field and is not aware of what you want to show. And if your figures are compatible with black and white, this will be already a good thing. Some things also a bit more what I feel like, what my opinion is regarding labels. I see a lot of people use labels such as A and one single slash. I'm not very fan of this. I prefer to use either the letter or the letter with a point, or if you submit to science, you use, or Joule, now you use capital letters. Again, it depends. What it looks really weird is when you use a font size for the label, which is huge. It's even larger than your panel, and it is in bold. So be sure that your labels do not distract the reader. The labels are the labels are there to guide the attention to the panel and to know what are you looking at, but they do not contain any useful information beyond that. I see the captions as very important too. We haven't seen examples here of figures that cannot be understood without captions. So to me, the caption should be a standalone text. it should fully describe your figures and include relevant experimental conditions. And it would be nice always if your caption could include the main message. For example, the title of your caption is variation of temperature reveals crystallization of perovskite, something like this. And then you go into details into the captions, into the specific caption for each panel. But the more you can convey in the caption, the easier it will be for the reader to understand the paper. So I find that if the reader could understand the core of your paper by just looking at the title, abstract, figures, and captions, you will have a lot done already. So this is just to show what I do, but again, as we say in Spanish, cada maestrillo tiene su librillo, which means like everyone has their own way of doing things. If you remember Brandon's presentation, he also said like just choose your favorite tool, the tool that you are more accustomed to working with, and just do the best with it. So in my case, I use normally MATLAB or Origin to process and analyze the data. There are also important aspects in these softwares, which is the use of templates. You can define a template to the figure format that you like, to the font size that you like, to the line width that you like, and then use this template all the time, and you don't have to change this for all the figures, which is a pain. Then I would recommend exporting this always as PNG and PDF, also as native software. For example, software format. For example, in MATLAB, you have the FIG format, which is easier to modify. Then for the schematics and for the modification of these other data panels after they have been made, I normally use Inkscape, which is free. It's excellent, I think. It has some flaws, but in general, I think you can do most of the things that you can do with Adobe Illustrator, you can do with Inkscape. It allows you to create and modify vectorial graphics and also to assemble the panel. So I see a lot of people uses PowerPoint to assemble the final figure sets. I mean, which is nice, but it's not the best. I think I would recommend people learning how to use Inkscape and assembling their figure sets in this kind of vector-friendly software. For 3D schematics, there are different options too. You can also use Inkscape to do the 3D schematics, as I will show you later. But most commonly used suites are 3D Studio Max, Blender, Rhino, and again here it is important that you save your files in the native format so you can edit it, and also that you export them as PNG with transparency channels. This will help you, for example, combine different panels later. For figure assembly and export, again, I use always Inkscape, but I mean, Adobe is equally nice. Again, Photoshop, PowerPoint is very limited in the sense that you cannot export or import or edit vectorial graphs in the same way. So I'll just show you some examples now with Inkscape, which refer to the editing of some figures. Okay, so I just go to Inkscape. Some examples here. So this is a figure from a recent paper we published in March, I think. Can you see the screen now? Yes. Okay. So you have different panels here. One thing that I find useful normally is like if you export your figure in PDF and you import it in Inkscape, and then because we normally also work with collaborators, maybe they send you the figures in the worst format. You could just harmonize the file, the fonts and everything using Inkscape, for example. So you can import a PDF here. I think this is going very slow because of the of the Zoom, but I hope I can show you. So it crashed, I think. Okay, when you import files in Inkscape, you could just select the access, select the access You could just change the labels or change the fonts. Here you can change the font size. You could also change the line width, for example. Here there are different shortcuts. So for example, in Inkscape, you press Shift Control F, you enter into this menu, which is the one you use mostly. You could just change the line width. You could change a lot of things. This is very useful, I think, for people doing their PhDs too. So if they export all the graphs in PDFs, they might have changed their style during the thesis, and then when they write the thesis, they can harmonize. They can harmonize all the graphs to look similar. What I also find useful is for microscopies. I think because of it seems. Well, it's not working very well because of the many sub. Okay, here. So what I want to show you is, like, for example, when people have microscopies. Yeah, I use 3D Max to draw figure 8. Microscopies, usually you have SEM images or you have TEM images. They come with a native bar in the bottom showing data, like what microscope did you use, what energy did you use, what magnification did you use. This data is important to have, but it's not necessarily crucial to show it in the main text. So what I typically do is, because these bars also have limited resolution, is to import the SEM image to Inkscape, and then okay, I'll maybe show you the example with other software. Okay, with this. Okay, I think I should get a better computer because it keeps crashing. Okay, so what I want to say is that you can import the SEM image, and then you can crop it to the area that you want to show, and then you could just copy the color bar. Sorry, not the color bar. Copy the scale bar with the same size, of course. Just draw a rectangle of the scale bar and write the scale on top. So this can help you improve, I mean, the quality of your SEM, of your microscopy images. So I will share these figures with you in the package so you can play with them, because it seems I cannot actually modify them live. So now just going to figure making of, yeah. So this, for example, I cannot edit it for some reason, like. Okay, yeah, I can. So this all I draw by Inkscape, by hand, just by drawing forms and just putting different layers. So you could get kind of nice, already nice looking images, already with Inkscape by itself. So you see this flask with very nice material inside, very nice quantum dots. Contains different layers that I cannot edit now. Okay. And then by adding these layers on top of the other, it gives you the looking of a 3D image just by playing with the illumination. You see there is like a trace of light here, another trace of light. You just play with transparencies and this kind of stuff. So again, these vials of quantum dots, the same. You have this light in here, in this bulb. You have the same. You have, I mean, just by playing with transparencies and polygons and stuff, you can already make decent looking quasi 3D images. So since this is not working very well, I will just share these files with you. Okay, and if you have any question, we can address them offline, or by email, or we could have another follow-up tutorial if you want. Now, just regarding 3D Max, there are very, very simple things that you can do to improve the quality of your images with 3D Max. I'm not familiar with Blender. I think Min Jae and others are more familiar with it. But for 3D Max, what I can tell you, it is basic that you go and select the right rendering, okay? So you go to the rendering menu, you go to render setup. This opens a menu which allows you to select the type of renderer. You go to the bottom of this menu, you go to assign render, and it is very important that in the production and active shade renderers, you don't use the default rendering. Just use whatever says mental ray or something ray renderer, okay? This will open the room for more materials and better looking materials compared to standard renderers. So again, go rendering, render setup, assign renderer, and change the renderer to mental ray. Another important thing is because normally these renderers use a black background, they are not really useful for us. So you could go to rendering environment, and in the environment you could change the background color. So you could say, okay, my background color should be white. And then you could just make some material. For example, you make a sphere. When you make a sphere, you could change the different properties of the sphere in this edit menu. You could also make, I don't know, whatever. This is some basic stuff. You have more information on the supporting stuff. So just, okay, in 3D Max, you could, lighting is very important in 3D Max, super important. So that's why it's very, I think it's better not to mess up with the lighting unless you know how to do it, because it is the case, it is easy for you to destroy the image by playing with the lighting rather than improve it. So you go into lighting, you have to take your time to learn how to do it. If you do it, that's amazing. So the last advice for the 3D Max, because you use this mental ray renderer, you now can have access to more materials. And in my experience, the better looking materials are those under this tab, mental ray. You could go to Arc and Design. And once you go into Arc and Design, you have different templates here. You have, for example, I don't know, translucent frosted glass. Frosted glass, you see it here, frosted glass. You could see that's some transparent. You could just add it to the material. And let's go to the other material and select, I don't know, whatever. Let's say car paint. Okay, take some time, and then assign. You could change a lot of parameters here. It's just to show you an example. Okay, assign it to the scene, and then you could just render the production. It will take some time depending on your how complex your image is, and how what's the resolution that you want to export the figure at. You could make it more accurate if you increase I don't know, this. You could play with this, but in normal, I mean, for scientific figures, it is not that you are recording and preparing the next Toy Story movie. So this is normally enough, the settings. So you see, you get this image. You could play with this. But in general, by using these tricks, you get access to a more, like a richer set of tools compared to the standard. Okay. Now going back to the presentation. So we saw some examples of Inkscape, which unfortunately we couldn't showcase live, but again we can discuss offline. For 3ds Max, we have seen how to change the renderer to mental ray. Again, 3D Max is not free, but for people at U of T and other student like academic institutions, you can get a free copy. If you go to this website and you put your U of T address, you get a license. You can use this for free then. So it's a good thing. Again, you could select for the renderer, select mental ray. For the material, select Arc and Design. Change the background. You could export your initial images in lower quality until you are satisfied, and then make the final good images with higher number of pixels. And always export with the alpha channel so you can combine it with Inkscape later. So now to conclude, thanks to Armin, he provided some of his figures for the new paper. So we can give some feedback to him on how he can improve these figures. If you want to comment on this, please write on the chat, and then we'll go one by one. So Shasha, do you mean in the bottom, in the B?
Yeah, maybe it's supposed to show that there is no aluminum and gallium, but it's just black.
Armin, are you there?
Yep, I'm here.
Okay.
So the second one is a porous structure which has both copper and aluminum, but it's like kind of alloyed. And the third one is we galvanically exchange some of the aluminum with gallium, so you would have uniformly dispersed gallium on the surface. So, yep.
Okay, what do you mean being changed by Ali Yassin?
Galvanic exchanges, like we put in the solution of gallium, and some of the aluminum will leach out and will be replaced by gallium.
So, Bing Chen, what do you mean by anti-aliasing?
I mean, the edges, if you look at the plots, the lines are very zigzag at the edges. So you can...
You mean in this panel?
Allies.
In this panel?
Yeah, that panel, 1B.
This panel has, like, you zoom it, you will see that it has, yes, looks like limited resolution. Again, this is a draft image, so I'm sure like when Armin export this in the final format, it will be with higher resolution. But yes, like there seems to be a problem with the line quality, which is very zigzaggy. There is also a problem in the x-axis. Is this the standard way of plotting the angle, or should you comment on the units? Should we include degrees here, perhaps? Armin?
Sorry, it's a little bit later.
Okay, I can tell you what I found, and then you could add something. So first thing I found was HCl is all in capital letters here. So I think that's a typo, but that's fine. When you say weight percent, I think, is it the standard way of saying weight percent, like just W and the percentage, or is just W/W?
Yeah, it's weight percent.
Some people have also spotted like the text is overlapping with the figures here. Like partially the alloying is touching this. So you could make the whole panel a bit smaller without losing the message. It would be nice also if you could add in this last figure here, what is aluminum and what is gallium. I know that the content is very little, so it might not be needed, but if you include it, you should use a color that kind of matches the ADX mapping that you have. Okay. Scale in C to me looks a bit thin, so you could make it a bit wider, and also you can include it here or include it in the caption. That's fine, but include the what is the actual number here. Okay. I think Maral is saying that XRD is too busy. I agree. So it's I mean, XRDs are always busy because they have lots of stuff. But I think you can also be more creative in the. I've never seen like it would be nice like in this XRD, for example, you could have this panel, but below this panel you could have much narrower panels with bands for copper and the other alloys that you have, showing at which positions each crystal configuration appears. Do you understand what I mean? Like.
Yep, I understand.
I can send you an example. In any case, also for this 3D schematic, I have found an example for you in YouTube okay, that you can use to learn how to make this sphere very easily in 3D Studio Max, okay? So if you download 3D Studio Max and follow this tutorial, I can also help you, but I think this is a good example for you to learn. I forgot to mention that I'm not a 3D Max expert at all. So what I normally do is I start by looking in YouTube. What is the most, convenient way to draw what I want to draw? So it always takes time, but it's always good to learn. So I'll send you some example, and if you need help, I can help you, but I think it's a good opportunity for you to learn, okay?
Okay, thanks.
So more comments. Sphere size is distracting me from other figures. Do you want to comment on this, Alan?
Well, I think it's quite big and it's distracting me from the ACM images through them.
Mm-hmm.
If it was a little smaller, I could focus more on the ACM images, I guess.
Yeah, a good point. Yeah, if you made it a bit smaller, it could be, make your figure fresher. So don't, exhaust your attention on your eye. Sometimes white space is important in the figures. As I was complaining about white space before, but white space is something that you have to manage to also direct your attention, as Maxud was saying. So you say, I want you to look here first, but then go somewhere else. Just I saying something important about the crystal plane names, that they should go in brackets.
Yeah, so oftentimes we use like 111, 100 without any brackets, but it's just forbidden to do so. Like the brackets have special meanings. There are round brackets, there are curly brackets, and there are square brackets, and they all mean different things. And without brackets, the numbers just don't mean the crystal planes.
Mm-hmm. Arrows in A can be thinner. That's true. They don't add very relevant information. Align figure with A with BCD. Yeah, alignment is important. That's something you can also do in Inkscape. You have a built-in scripts that you could just use to align your different items in the figure. Dimension of a horizontal can be equal to B plus D horizontal. Yeah, so that's very important. Maxud, you want to comment on this?
Yeah, sure. So the A panel, the left edge is a bit going over B panel on the left, and then the right side is not aligned with the D. So that can be aligned. And also the X-ray in D, I think the X-axis lost some resolution. This sometimes happens when you export data from X-ray. So sometimes it doesn't take enough numbers after comma.
Mm-hmm.
So you need to be careful when you translate your data into Excel or into Origin.
That's a very good point, yes. Are you satisfied, Armin, with this, or you want more feedback?
Yep, thanks.
Again, I'll send you and everyone the example for this sphere. It's very easy to do, and it's very easy to learn, okay?
So Armin, when you submit your paper, you should exclude us from reviewers.
Sure.
Unless you implement all of our comments now.
Yeah, I try to implement all of them.
Okay, Vincent is saying comments on the tick direction. Want to use pointing towards, outwards or inwards. I think it all depends. There is not a convention for this. I find the only important thing is that you are consistent. So it looks weird if you have all the ticks going in the x-axis inwards for the major ticks, and then for the minor ticks going downwards, or you have all the labels in and out. So to me, it's all up to you, but be consistent. Depending on the journal, they have different conventions. You might look like, I think Nature Photonics has them to the outside, I think, and other nature journals to the outside. Science is not so picky, I think, for this, but again, it's up to you, but be consistent. I think there is no rule for this. Font size, okay, different font sizes. Tao Peng is complaining, but for the sake of time, let's move to the other figure. Any feedback here? There are many things here. Set in C, okay. Panel sizes are very different. So what do you think about the order of the story here? So you start from panel A. In panel A, you have Faraday efficiency versus time. So I guess a good title for this caption would be mechanistic study of catalyst degradation, perhaps. You have in this kind of plots. I mean, that's again depends on the person, but I find that more useful if you plot the order of products is important. I mean, you start showing in the bottom methane, okay, and then you choose hydrogen, and then you suddenly go to ethylene. So I think if hydrogen is what increases because it's the bad thing, you could put it in the top or in the bottom. But putting it in the middle of ethylene and methane, I think it can, you know, be optimized if you did it otherwise. Also, the choice of colors you can improve. So if hydrogen is your unwanted product, you could put it in white, perhaps. What is to me more striking is in panel B, you have to export this using, I mean, either vectorial figures or high resolution. You see, this is again very, very limited resolution. Okay. Color not consistent with other, use line to show trend in A. Can you comment on this topic? I don't know what you mean by this.
Oh, for figure A, they use a column, so it's difficult for reader to see the trend. If you use line, we can see the peak. The peak is in 5 hours, but if you use column, it's need reader take time to understand the trend.
I mean, that's a good point. That's again, you realize like there are many different opinions. Like it's very subjective. So that's a good point. But you have to choose the graph in the end that is sufficiently clear, but also that you like. So you really like these bar plots. I think they're not necessarily bad, but Taopen makes a good point. Like maybe some people will not get this trend so easily.
Yes.
What I find that would improve the readability of the figure a lot is combining the SEM images and panel C. So you go first, you show A, you show FE versus time, then you go do some materials study and show what happens. And then, you know, does panel D correspond to panel C top?
Right.
So why not? Yeah. Why don't not put panel D just besides or on top, panel C top, and panel D just, you know, conveniently placed. So it's just, you know, in the same way in the paper we shown in the beginning, like we have shown in the beginning the Nature Nano from Moskowitz. So have the SEM image placed near to the cartoon. And you could even have a label saying before and after then, so it would be easier to understand. Okay, anything else? Okay, I think this is the last slide. So is there any question regarding the overall presentation? Again, I'll put some, I mean, the video will be on Google Drive, and there will be a lot of additional resources. And you can reach me if you have any questions with your files or something else. So is there something that you would have wanted me to talk more about or to develop more, so we could prepare a follow-up presentation in the coming weeks? Nope. No questions? Okay, thank you. So you don't have any questions. Let me thank you again for for attending this seminar, and also for providing very useful feedback, and for being very energetic during these discussions. I think it was very useful for Armin's images and for everyone. Again, I'll put everything on the Google Drive. If you have any questions, just write me, okay? You have my email. Thank you for your time. Bye-bye.